the sharing. You think if you have any questions before I start? Meanwhile, I prepare the. We usually take a few minutes before we start, just to make sure that everybody's in. Seems to work. What is this? This is the last lecture. It's checking where we stop. So this is lecture 7. No questions? I can start. I'll wait a minute still. Today is the 23rd. So we talked yesterday about spontaneous symmetry breaking. And let's go on and talk more about the Goldstone, as it's often called, which should actually be called Nambu Goldstone. Mechanism. Which was far more interesting than the discrete case. Because of the fact that there was actually a very interesting dynamical phenomenon associated with the vacuum, with the strange vacuum that the theory forced on us with our choice of variables, of the parameters. And that is the emergence of massless particles. Massless particles are fascinating objects. And it had to be strictly massless, remember, not light, strictly massless from the principle of the theory. Let me remind you, Lagrangian, of course, there is a kinetic energy. There is a potential. And let's make the theory more interesting. Let's add something I will call a Yukawa sector. Let's add a fermion. In other words, I will add an interaction, okay, V of I, just to remind you, was lambda over 4. Phi star 5, which is phi squared minus V squared, everything squared. This was the most general quartic potential. The crucial thing is the minus sign. Made all the difference in the world. It's interesting how much extraordinary rich physics can emerge from a sign. And the Yukawa interaction would be analog of what Yukawa wrote for the pions, and that's why a historic name. It has nothing to do with Yukawa. When Yukawa thought of the strong force in the 30s, he wrote the interaction between the pions and protons. So it's just history. So there is some Yukawa coupling. Sometimes you write even the label that it corresponds to the fermion psi, or you just write a small y, and then you write the interaction of this form, psi bar psi phi. You have to add a Hermitian conjugate to make, of course, the Lagrangian and the Hamiltonian, eventually Hermitian. This is our theory. I didn't even have to tell you that the field is complex. It's clear now that it's complex if I assume that there is a symmetry. Everything will emerge from this Lagrangian given to you. Okay, this is our starting point. The kinetic energy is canonical. There is nothing strange. The strange thing here is the minus sign. And an interesting thing is, of course, the emergence of the symmetry, because notice that there is a symmetry here. Let me rewrite this to make it more clear. As you know, psi bar psi is actually psi L bar psi R phi plus. So I should have written like this, really. This is confusing. Let me not even write it. Let me cross it, because the correct way of writing should have been this. I'm sorry. I won't erase it. I take it back. It should have been written like this, plus psi R bar. Otherwise, it looked that phi was real the way I wrote. I should have been very clear. This has to be phi star in order to have a symmetry. This is now Hermitian, and it manifestly possesses the following symmetry. What it is, it has what we call a chiral. Someone knows why we call it chiral, U1? Chiral means that the properties of left are different from the properties of right. For example, the weak interaction standard model weak part is chiral because you have nu EL and ER. This is manifestly chiral. Left is different from right. For example, QED, where the photon couples like this, is not chiral. It is manifestly left-right symmetric. It's strange way there. Usually the name is often vector-like. The name becomes vector-like. Why? Because you can write this as psi bar gamma mu psi, which looks like a vector, a 4 vector. This is a 4 vector. Hence the name vector-like. If L is different from right, there is no way you can write the vector. So once again, chiral, I should have written explicitly, is this interaction, nu L bar, gamma mu EL, W mu plus. So let me write what I mean by that, just to be clear. Nu R bar, gamma mu ER, W mu plus does not exist. So this is chiral. Okay, just to make sure that the language is clear from now on. Simply, there is no right-handed part. So I can never write this as a vector. It has this funny L label, and it has 1 plus gamma 5. So either the world is chiral or it's vector-like. This interaction here is chiral, right? Because left and right will have different charges. So imagine the symmetry. I have said that 5, so let's going back to our Lagrangian, our U1 case. So we have a U1 Lagrangian 1 with 2 plus 3 possesses a symmetry. U1 global symmetry. I said, I took yesterday phi goes into e to the I alpha phi. I fixed the charge to be 1. Q phi is 1. And that tells me, I go back and read here in 3, what do I discover? That I have a choice, of course. I don't know a priori. I have a variety of choices. For example, there is a symmetry. For example, I could write that psi r, I find the symmetry, goes into e to the I minus alpha over 2 psi r, and psi l goes into e to the I alpha over 2 psi l. Let's check it. Check. We have psi l bar, psi r phi. This will go into psi l bar, e to the minus I alpha over 2. This is a complex conjugate. Psi r has e to the I alpha over 2. Psi r, no minus, the way I've chosen. And then there is e to the I alpha phi. So this, and this cancels. And this is psi l bar, psi r phi. It's invariant. It checks. There is a freedom here in choosing the charge of psi l and psi r. The reason is that there are actually two symmetries. The reason there is a freedom, there is also, so this is the chiral U1. Left is different from right. Notice here above. Manifested different. You can tell me, look, there are many symmetries, because I could have also chosen, or, so this is 4. Look at 4 prime. I could have chosen phi goes, that I fixed yesterday. So let me keep this. After all, one charge I can fix. Then I can say that psi r goes into e to the minus I alpha psi r. And psi l goes to psi l. It looks like a new symmetry, right? This is trivially invariant. Then psi l bar, psi r phi goes into psi l bar invariant, e to the minus I alpha psi r, e to the I alpha phi. And this is invariant. This checks. And so on and so forth. I could have taken psi r invariant for 4 double prime. Phi goes into minus I alpha phi. Psi r goes into psi r. I can choose anything I want. Psi l would then go into e to the I alpha psi l and so on. So you may say, what is going on? How come so many possibilities? Well, the reason is there is also a vector-like U1. And so any linear combination will be, this is very important. There is a vector like U1, which has the form phi goes to phi, psi l goes into e to the I beta psi l, and psi r goes into e to the I beta psi r. This is trivially an invariant because psi l bar psi r phi goes into psi l bar, e to the minus I beta, e to the I beta psi r. It checks phi. Phi is invariant. Notice, however, this is interesting. This symmetry is not interesting to me at all, because what happens when phi is non-zero, as we've seen yesterday, spontaneous symmetry breaking. U1 vector-like, let's call this U1 vector-like. There was also U1 chiral. This implies U1 vector-like unbroken. Obviously, it carries no charge. Only U1 chiral gets broken. But because of the arbitrariness of beta, I have various possibilities. I can call this vector-like. It's just a definition of what I mean by the vector-like. Notice, you know what this vector-like symmetry is. It's a fermion number. The Dirac-Lagrangian always possesses that I added. So this vector-like symmetry is a fermion number. Fermion number is conserved in theories that we write, and they have the form of psi bar psi. That will always conserve fermion number. This is of the form psi bar psi, psi L by psi R. Okay. So what we said yesterday, what happened, okay? What happened at the end of the day from the potential, so the summary of yesterday. So what we learned, I wrote phi as, after studying the potential, as V. I took a point. This is the point that belongs to a vacuum manifold. Vacuum manifold was set of all points phi 0 square. Remember the minimum of the potential, which is V square. So this is vacuum manifold. I took the point and I said the physical fields are the ones that live around the minimum. And yesterday I found out that mg is 0. G is what you called a Nambu Goldstone boson. It had to do with the fact that Q acting on phi 0 was actually phi 0. The vacuum carries charge. So when vacuum carries charge, this means that the symmetry is broken. And every time vacuum carries charge, there is a consequence that's an equipotential surface manifold, a circle. Along that circle costs you no energy, and the mass of the Goldstone boson tells you that that's precisely what is going on. It is often called Goldstone. And then also we found out that the mass of the Higgs, it's a very interesting particle. I call it Higgs. Sorry, I shouldn't call it Higgs, but I just to anticipate, there is a real scalar field whose mass is equal to lambda V square. Someone is not muted. Please, you should mute yourself. Unless you want to speak. This is what should be called, as I said, Goldstone scalar. But it's often called, it will become Higgs. This is scalar. By the way, G is pseudo-scalar, we'll see in the moment, okay. Well, I've given them the name, so why don't I say boson before being precise. This is surely boson because 5 is a boson. Okay, let's see the properties. We'll see the properties. Let's look at Yukawa interaction, which is a Yukawa coupling times psi L bar, psi R, then V plus H plus IG, agree, plus Hermitian conjugate. Well, let's be, I should not be lazy, just for you to be sure. Once it looks like this. Minus IG. Which means that I will get Yukawa, psi L bar, psi R, plus psi bar. This is a very important part. This is what happens in the standard model. This is very, very important. V plus H, precisely the situation later on in the standard model, plus Yukawa. There is a factor Y, psi L bar, psi R, minus psi bar, psi L, G. Am I right about the signs? I think I am. Notice here, let's go back. The way I wrote this Lagrangian meant that left and right fermions had different charges. I had a freedom because of the extra U1 symmetry, but it was always chiral, the symmetry under which phi transforms. Like whether I take 4 or 4 prime or 4 double prime, the chirality meant, you see what meant, let me just write it, okay, because the U1 chiral, the way I wrote, had phi transform is e to the I alpha phi. That meant I could not write the mass term. This term was not allowed because left and right fermions have different charges. I had no way of giving the fermion of mass. Not allowed. Which is the situation we encountered in the standard model. If you remember in the standard model, let's go back. You may forget these things. Let's be patient and go back. Where is it? I gave an example. Look at this here. Look at ER. EL and ER, they are completely different. One is a singlet, the other lives in a doublet. There is no way an electron can have a mass in the standard model. This is a serious problem of the standard model that we have to solve. This is what we are developing the theory for. And I want you to emphasize that this U1 example, the prototype I'm doing here, has all the features that we will encounter later. You learn now, the rest will just be group theory, but the physics is here. There'll be modification when I go from Nambu-Goldstone to Higgs, but this instance is here. I couldn't write the mass term, but I got it. You see what I got? Yukawa interaction is very interesting. There is Yukawa V plus H, left and right combined to give me psi bar psi, plus IG, IY, there'll be a minus sign. My left, right are 1 plus minus gamma 5 over 2. So there'll be minus sign, and I'll get psi bar gamma 5 psi G. Notice that this is an axial kind of what we call, there is a gamma 5. So this is a pseudoscalar, what we call pseudoscalar. We give it a name when it's gamma 5. H is a scalar. It couples to psi bar psi. Scalar. It's parity even. This is parity odd. And what I have is m psi bar psi. I got a mass, the beauty of the Higgs mechanism, and I have this so-called Higgs that couples like, let's write it. Okay, why don't we write it? Yukawa psi bar psi H minus I Yukawa psi bar gamma 5 psi V. What is M? M is Yukawa V. Remember what I said? With spontaneous symmetry breaking, the mass of every particle will be proportional to V. Must be proportional to V. This is the only dimension non-zero parameter. And the constant of proportionality is the interaction with H. So you see what H does. H, the guy that has vacuum expectation value non-zero, that lives around the vacuum expectation value, provides the mass to particles in question. That will be standard model later. And this is important, and couples to mass. Why? Because Yukawa is M over V. Therefore, you see what we got, that Yukawa interaction, let's write it, is there is a massive guy, there is a Higgs field that couples as M over V. I'll call it Higgs, it will be clear later, minus, again, the same thing, M over V. Also our Goldstone, Nambu-Goldstone boson couples to the mass. Goldstone bosons like couple to the mass, and there is 1 over V. This is very important. They share the property, okay? Remember, under parity, psi goes into gamma 0 psi under parity. So psi bar psi goes into psi bar psi, trivially. This is a scalar. And psi bar gamma 5 psi goes into minus psi bar gamma 5 psi because of anti-commutation. This is a scalar. This is called a pseudoscalar. This Higgs is a scalar, G is a pseudoscalar, okay. So the breaking group continuous symmetry provides an extraordinary prediction that there will be a massless scalar coupled to your fermions, which will be electron or an up quark. Now, an interesting thing. So let's talk a few words. Well, let's summarize. 1 solves the Nambu-Goldstone, the spontaneous symmetry breaking. Spontaneous symmetry breaking solves the problem of mass. The symmetry forbids it, but this spontaneous breaking allows it. Mass, this is beautiful, becomes dynamical. What it means, that Higgs couples to mass. We'll talk about it a lot. It's not just a parameter, it gives me now, you see, because of this Yukawa structure, mass tells me about the interaction itself. For example, I mean, this you can understand even here. If Higgs is heavier than the fermion, Higgs will decay, and it typically is. Think of the standard model, it will decay into psi bar psi. I mean, just to remind you, in the standard model, for example, it's around 125 GeV. And think of this psi as an electron. Typical mass is small, it's 0.5 MeV, so this decays. And I can compute the decay rate, gamma Higgs into psi bar psi for different fermion is proportional to m squared. This is what I mean dynamically. You give me the mass, and I can compute the decay rate. I cannot overemphasize this. We have here at our hands, we have the theory of the origin of mass. Because you can ask me, how do you know that I live in this funny vacuum? Are you going to measure the charge of the vacuum? We'll talk a lot about it. How in the world? You know, if I tell you that we live in the vacuum in which, let's go back here, that V is non-zero. How will you and I know that? Imagine a fish living in the water. How does fish know that it lives in the water? It cannot know where it lives. Dolphin knows, because dolphin can get out of the water, come to the air, and of course, they can talk and say, look, this is very different, okay? Here we breathe completely differently. But the fish, you know, a fish unfortunately can have an epiphany when it's fished out just before dying, a tragic epiphany, knowing that there is another life. So you may say, how will you ever know? How can you become a dolphin? I'll talk about it. It's not easy to be a dolphin. How will you know that you live around this vacuum? How will you know that this spontaneous symmetry breaking gives the mass? Well, I know. I know because I know that I have a theory of mass through when Higgs decays. When Higgs decays into any fermion FF bar, I can compute, as I said, gamma H FF bar proportional to M bar. So for example, I can tell you that gamma H coupled to mu mu bar, decaying into mu mu bar, H coupling to E bar is very easily computable. It is M mu over M E squared. And I can do it for all the masses. So this way, we actually probe the spontaneous symmetry break, which means that we probe the origin of mass. This is a great virtue of the standard model, because this is what will happen in the standard model. We'll talk a lot about it, okay? But I want you to get a flavor today already. Okay. Any questions, please, here?
I have a question.
Yes.
So I can hear you. I don't know why.
Sorry?
No, anyways, I was just asking, in the coupling of, I mean, in the Yukawa coupling, we have the coupling constant turns out to be M over V, where
Right.
V is the vacuum expectation value of phi. So I was just asking, is there any way to measure the vacuum expectation value V? I mean, here we take the ratio and see that the ratio, the V gets cancelled.
Very good.
But
What is V?
yes.
Precisely. Very good. Very important question. How to measure it? Well, remember, it is, of course, a question of normalization, because I wrote, let's not worry about that, but just to remind you, I wrote phi is V plus H. I could have normalized my field phi differently, okay, but that's a detail. This fits with the original normalization, okay. So once we do that, we stick to that normalization, you have this very important question. What is? I was thinking whether we tell you or not. I was waiting for the question. Per se not, but we can do a little more. Because remember that mh squared is 2 lambda v squared. This is very important. Another times when lambda enters. So although I cannot measure it, and that went with the interaction. Remember, there was an interaction. Remember that in the potential there is h to the 4th. So you can measure lambda. It's not easy. But you discover your Higgs, that I call it, and then measure scattering. So we can measure lambda. So we can then, and we measure h, measure. So I can extract V that I couldn't know from the fermions. So this would give me V. I cannot predict it theoretically, of course, because it's the parameter that I put by hand. Remember, V was there from the beginning, that I cannot predict. That was my dimensionful parameter. As you said, that there is no way, where would it come from when it's the only, what happened here? Oh, sorry. Let me just, why was it there? Okay, something strange happened, I'm sorry. So I can extract lambda, and from mh plus lambda, I can get V. So it's not that I predicted a number, because I didn't predict mh. But at least from an independent path from the fermions, I can know what h is, for what V is. That I can actually do a little better once you give me this information. By the way, I can even do better than that. In the standard model, you will show to learn later. So stay tuned. And keep watching our programs. We will learn that MW is equal to G times V. And you know G, that's a gauge coupling. So from MW, which you measured a long time ago, measured in 1983. And so you know this number perfectly well. And G, you can determine V. Once again, you didn't predict it because you cannot predict your own scale. That's impossible, which was the input. But once you measure W, and I'll show it, W was enough, you will get the Z mass, everything else will be predicted, and all the fermion masses will then be fixed by the mass and MW. In other words, I will be able to write what will happen, that Yukawa couplings will be G over fermion over MW. So I hope that answers yours. This now is, I can do better than the ratios. I will actually know this in the standard model. I'm whetting your imagination. Of course, we didn't do the symmetry breaking in the standard model, but at least you will see how it's going to happen. And therefore, I can actually predict the decay rate of the Higgs into every fermion. And that's going to be your homework. I hope that we'll have time to do that one, okay? If not, I will do it for you so that you appreciate yourself how this is an ongoing research. I can also tell you today, and come back to it, that LHC has actually probed this, And we know today that W, Z, let me tell you, we already know that. This is the beauty of the LHC. Top quark, bottom quark, and tau get the mass from the Higgs mechanism, from this spontaneous symmetry break. This has been proven. We have measured these couplings. We have measured these decay rates. This is now, for sure. The second generation is being probed as I speak now. And the results will come in due time. The first generation, you will see it's hard. Okay, that's later. But did I answer your question?
Yes, Professor.
Good. Please ask me here, because this is your best bet to clear your possible confusion. I can't overemphasize this. It's not appreciated enough. You go to meetings and the seminars, every Dick and Harry. There are people actually who call this in the standard model fermion mass problem. There are people who say this. But why is M electron equal M electron and not something else? Okay, I think this is crazy to ask this question. And some people say we should do better than that. We should predict all the masses. Okay. You can imagine people say this. I myself believed in this many years ago, and we tried hard, and you realize as you go along that you're confusing yourself because you start building models that actually assume what you are going to predict. I'm not going to address this question. I don't care why electron masses. I'm interested to probe the origin. Okay, what we need, it's the issue is not why the number is of it is. This is not physics, in my opinion. Not really. The physics is not to answer such questions. Physics is how to correlate say electron mass with a new physical process. Not why it is to it, but how do you correlate? Physics is about correlating different physical processes. Einstein didn't tell you what the distance of the Earth from the sun is. It would be crazy to ask Einstein to do that. But he will correlate, well, Newton, sorry. It would be crazy to ask Newton, but he will correlate that to the falling of stones and so on, to the plan, to whatever. You will learn a lot. Think about doing physics. So please, don't get fooled by false prophets. And I am afraid that you will be, because I can see from your interest that you're likely to be fooled by people who promised you gold. You will have some kind of final theories. You will explain why, today I'm here and you are sitting at your home and so on. That's not science. This is physics. And the standard model, in this sense, the theory that I gave you, it's a beautiful example of a physical theory. I correlate the mass of the electron and the muon and the tau and the bottom and the top to the decays of these fascinating particles, okay? The Higgs boson. You can imagine the most of the time, the bulk, the crux of what I'm saying here is going to be about the Higgs, obviously. That's today's research. This is physics. This is a task of physics. Okay. What else to say here? Notice an interesting thing. We don't have this Goldstone boson, but there is a similar generic property that, just like the Higgs, the Goldstone boson couples basically in the same way, but it's pseudoscalar. That's the only difference, couples to gamma phi. But again, if you know the mass, you know how the Goldstone boson happens. So I have a question for you guys. Mg is 0, which means a long-range force. You agree? When the mediator is massless, you get a long-range force. Just like photon mediates electromagnetic force, which is long-range. Graviton. So we have a new force like gravity. And let me be more precise. And it's coupled like m over v, I, g, psi bar, gamma phi psi. How come I can speak? Am I crazy or something? You know that we know so is this changing? This changes the laws of gravity. Newton was wrong if there is a Goldstone boson, number Goldstone boson. Is this possible? Just like graviton. You know, if you don't move, graviton couples to you proportional to your mass. I have a new mediator that gives me the same long-range force, and that should not be possible because gravity has been measured fantastically. We have experiments at the distances about a meter or so. Even smaller distances, people are going to the millimeter even, but at these distances around a meter, gravity is well probed. And Newton is right. So what's going on? How can I talk about instead of saying this is crazy, I should forget about that, about the massless particle coupled to mass. Someone wants to try? It's a bit non-trivial. The answer, I'll start giving a hint and answer. Question, answer. Simply G couples to spin, and then let me explain it. What I mean is the following. To understand, I'm asking about the static force. So I want to go to the non-relativistic approximation. Small momentum, let's take P equal to 0 to see what is going on. Remember when you must have done it. I hope you have done it here also, non-relativistic limit of Dirac equation. Remember, if you work in the non-relativistic limit, you should flip gamma 5. It's better to work with off-diagonal gamma 5 and gamma 0 diagonal. This is what you should use to see what is going on. And then you will get that phi, I hope you remember, is u, v. And v is the small component, which looks like what? Who's going to tell me? It's close to 0, sorry. I should have said P over M, much less than 1. Who remembers the form of E in the non-relativistic limit? Possible that you don't remember? Sigma dot P over 2M, does it tell you something? This is small. So when P is 0, you get V equals 0. Because in non-relativistic limit, you're just talking about, when nothing is moving, you're just talking about rotation. All you need is a spinner under rotations U. You don't need a 4-component spinor. But you see what happens then? That psi bar, gamma phi psi, gets proportional because it's off diagonal to u dagger sigma dot p over 2m u, which is u dagger sigma over 2 u p over m, which is spin, the value of spin, average value, times p over m. So in other words, the interaction, which was m over v, psi bar, gamma phi psi g, notice what it becomes. It becomes actually the average value of your object you are looking at, microscopic object, spin, m cancels, times p over v. So in other words, when p is 0, no coupling. You can say p is never 0. For example, if I think about, the sun and the earth, elementary particles inside are moving. This is full of particles. You have some idea how many particles how many protons in a sun of Earth? Any idea? Tell me the number. Of course, there are many. So you can just say many, very many, okay? A lot. But roughly, please.
Into the 30 something.
More. I think around 10 to the 50. I think Earth is about 10 to the 50 GeV. We can check that, but I can bet around 10 to the 50. There are about 10 to the 50 proton. And the sun is about 10 to the 60 GeV. Okay, the mass. See, this is why gravity matters. Remember the gravitational potential, which is G Newton, M, M1, M2 over R. And then we said G Newton is 10 to the minus 38 GeV to the minus 2. This is 1 over m Planck square. Imagine in the case of the sun, you will get 10 to the 60 times 10 to the 50 over R. And you get a huge number. How much is this? 110 minus, okay, roughly 40, about 10 to the 70 over R. Huge number coefficient. This is why gravity matters. And this is why matter gravitates. Not because gravity exists really. It's so weak that you can forget about that. Proton never interacts gravitationally. It's nothing to worry about. When we talk about the physics, whether it's LHC or the next generation of accelerator, or the next to the next generation, whether you're talking about your children or your grandchildren or your grand-grandchildren, forget about gravity. But when there are a lot of them, of course, it accumulates. But notice what happens with the Goldstone, with the Nambu-Goldstone boson. It's proportional to the spin. Whereas the gravity or the Higgs, even Higgs H couples to mass. Why? Because psi bar psi will go into U dagger U. So the Higgs coupling will be, so Higgs will couple to U dagger U times m over v. It couples to mass. However, Higgs is heavy. So it's a very short range force. MH is 100 on the order of 100 GeV. So the radius of that force is 100 GeV to the -1. That's a very small number. That's about 10 to the -16 centimeters. Okay, forget about that. But G, which is dangerous because it's massless, couples to spin. It couples once again, we said, to S times P over V times U dagger U. And of course, particles in the sun, you know, because of temperatures or whatever, P is not zero, but the spin is basically zero. You see, spin is a vector. So the spin, like of the largest nuclei of the sun, is of order 1 or 10, I don't know. Whereas the mass of the sun is of order of 10 to the 60 mass of the proton. So the Nambu-Goldstone bosons are harmless for gravity. We don't have to worry. They could exist. Well, had they been harmless, I would say that V is extremely large, but I cannot say that in particle physics interactions, V will be the mass of some, fundamental particle like the associated Higgs boson. So for any reasonable value of V, I would be in trouble if this Nambu-Goldstone boson coupled to the mass. But it really doesn't couple to the mass in the non-relativistic limit. It couples to a vector-like quantity instead of a scale. Scalar quantity accumulates. So gravity matters because there are a lot of little guys inside you and me. I mean, how many there is inside me, just to remember my mass, just to remember. Mass of Goran, or your mass, is around 100 kilos on the order of magnitude, which is 10 to the 29 GeV. So remember that 10 to the 30 cannot be we are about 10 to the 30. Get a feel for the numbers. Get a little bit, play that sometimes when you're having coffee with each other and so on. Ask yourselves so that you appreciate it, why physical effects are sometimes important and sometimes not. Not because someone tells you in a class, but because you have a feel. So also when you decide to work in your research, get a feel for what you are exploring. For example, if you say to yourself, I'm going to work on quantum gravity, go and check, and you will find out that the effect is so small that it's like working on the possibility that my cup stays in the air. And you don't want to work on the possibility that the cup stays in the air. Okay. Okay, any questions, please? Before we stop a little bit.
Excuse me, Professor.
Please.
There was something you actually touched earlier at the beginning of the class. I would like you to revisit that part. And
yes,
that is the reason why standard model is said to be chiral.
Yes, I said. So just the sort of, the standard model in a nutshell. The standard model in a nutshell has a gauge group, which is SU2 cross U1, whatever. I'm talking about the weak part, okay, just the electroweak part. And then there is, so this is the gauge group of the standard model, very important, okay, we cannot overemphasize that, but even more important is its structure. And that is, just look at the leptons, and you have nu EL and ER. It is completely, it cannot be more left-right asymmetry. There is no even UR. ER is a singlet, and the SU2 EL lives in a doublet. So for example, EL has weak interactions, plus electromagnetic, of course. ER, no weak interactions, only electromagnetic. This is what I mean by chiral. Left is completely different from right. That may be the most essential aspect of the standard model. Think about it, the left-right symmetry is the first symmetry you saw as a child. And therefore, there must be some rich fix associated. This should be an issue you and I should think about, okay? You will see it has to do, for example, with neutrino mass, which is the door to new physics. But you can also see it just from our everyday life. We want to understand this left-right thing. And here we have a complete asymmetry, a fascinating thing. It could have happened that, for example, ER has a weak interaction, but much weaker, or a little bit weaker. No, it has no weak interaction. The father of the standard model, if you would take seriously these guys, Gleshow, Weinberg, and Salam, they would tell you that ER will never have a weak interaction. I can't believe that. I would bet you anything in the world that they were wrong. Well, I say wrong, of course, not complete. They are not wrong. They describe beautifully the world we live in. Is that what you're asking me? Or maybe you're asking something else that I'm not answering?
Exactly, that's what I asked. Thank you very much.
Okay. Any other question? Well, you may come with a question. Look, it's 12:03. So let's meet at 12. Let's take a break so that you can pose and so that I can pose and see whether I'm giving you the right. In what remains, at least I can be sure that I'm taking you where I want. And get some more coffee. Okay, see you at 12:10 then. Can you see my screen? Can you see me?
I can see you.
Something happened. Okay, I must have disappeared for a while. But we are back. Okay. Sorry, I don't know what happened. So let's start again. Let's share screen. I wonder what happened. You can see now? You can hear me?
Yes.
Okay, good. Okay. So, so I hope you got this, that the crucial thing was that Goldstone bosons are allowed to exist. Okay. Number of Goldstone bosons do not compete with gravity. But you know, they are massless. So once again, the coupling is so you see what had happened. Psi is a particle in question, which would be something like electron or a quark. And therefore, imagine that you have a star like sun. Sun is hot. There are interesting dynamical processes inside the sun, among other things. So even if you are thought of in non-relativistic limit, the P, for example, remember the interaction became proportional to spin and the momentum and so on over V. There is always 1 over V, whatever. Okay, even in that limit, you know, what would be the momentum V on average? It will be although the temperature, say, it's non-zero. So therefore, the Nambu-Goldstone bosons get produced by stars. Obviously, they are massless, so it's very easy to produce them. Like photons, that's what the star likes to do, produces massless particles through collisions. And you know, for a photon to get out of the star, it takes some time because it interacts, but it goes out. The stars produce neutrinos. As I'm speaking to you right now, there are billions of neutrinos passing through every centimeter square of your body, every second. Of course, neutrinos are crazy. They do no harm to you because they don't like to interact with anybody. But the bottom line is that you produce the number of Goldstone bosons. And that means that the coupling must be small. Otherwise, stars would stop shining, would lose their energy. See, there is no danger in producing neutrinos. They are weakly coupled. So this Nambu-Goldstone boson should also be weakly coupled. And you learn an interesting thing. There is still a limit on V. It's very interesting. You find out that V is much bigger than the scale of the weak interactions, which is MW, much, much bigger. Actually, you find that V is on the order of 10 to the 10 JV. I don't want to bug you with a calculation that you can imagine. That's a complicated thing, and you have to understand, the cooling of stars and so on. This is a product of a painstaking study. The bottom line is all that B must be large. In other words, if there are Nambu-Goldstone bosons, they must be associated with some very high energy new physics. With high energy new physics. Nothing to do with something a little bit above, beyond the standard model. I'll just mention some Nambu-Goldstone boson candidates that are very popular. I just wanted to give you the names, and sometimes in the office hours, if you want to know a little bit, I can tell you. People talk about axions a lot, myrons. These are the most popular, especially axions, something to do with so-called strong CP violation. These are just buzzwords, forget it. What we've learned, that if you are working on a theory behind them, it belongs to a very high energy category. I won't talk about them anymore. They're not of interest of us. We don't know. We have not seen any candidate. I am to teach you the standard model. And in the standard model, we are not breaking globally any symmetry, you will see. There will be basically just local symmetry. So I'm about to stop talking about that one, but I don't want to start a new subject. So just a few words about choosing variables. The art of doing physics is often choosing the right variables. For example, if you have a spherical symmetry, you can work in Cartesian coordinates, but don't do it. It's stupid. It's better to use spherical variables, coordinates. Or if there is azimuthal symmetry around the z-axis, better use 0 and phi, say, and so on and so forth, okay? That's what we try to do. So there is always this question that Weinberg says jokingly, make sure you choose the right variable. If you don't, you'll regret. So what did I wrote, so what are the possible variables? Remember, okay, what I mean here, let's talk about our scalar field. I have a dilemma which variable to use. I started with just a complex number, and I work with phi and phi star. So work with phi and phi star. But then we said I can work with phi 1 plus phi 2. At the end, it was not so useful. They didn't describe the motion around the minimum. Not really useful. Well, in the beginning it was. Okay, so I don't know how to say this. I should be careful. Useful to formulate. So actually useful for Lagrangian. This can also be useful for Lagrangian if you want to see that. But then I said we can also write, this is much more useful if you want to read of physics. This is useful to see what is going for you for the resulting physics, for the phenomena that you're going to study. Why? Because these are physical fields. Remember, phi 1 would be a tachyon. It was not a good field, okay? Physical fields with masses, mg equals 0, and mh squared positive. These are physical fields. I could also use the following thing. I could write, and sometimes it may be useful to see what is happening. I could have written also like this. It's actually some other G, but G prime or H prime. But let me just use the same notation just to notice. It's very important to have this vacuum expectation value because G carries dimension. As you know, dimension of H is dimension of G, which is 1, and the dimension of V is 1. We are in the units of mass, always. Units of mass. I could have written like this. A complex number can be absolute value in the phase. So you see, in this thing, Nambu-Goldstone boson is a phase. Notice that it's very useful, this formulation. Why? This variable. Why? Because phi square is V plus H square. So if you write like this, you see immediately that mg is 0. You don't have to do any calculation. G disappears from the potential. It's simply no G in the potential. So you can say, oh, but then there are no interactions. So you can say, what is going on? G does not interact. Is that true? With H. No, it's not true because there is a kinetic energy, which is 1/2 d mu G, d mu phi star, d mu phi. And now d mu phi in this formulation, notice, is d mu H e to the Ig over V plus I d mu G over V times V plus H. So there will be an interaction, of course, and it's derivative interaction. Notice, we just got the derivative here. So in other words, there is a formulation, the one that we have chosen. G has derivative interactions. All the interactions will be of the form d mu G over V. For example, in this information, even with fermions, you will get, if you play with it, you will get something like this. We can play with this, but we will obviously get a derivative interaction with the fermions too, and it looks very different from the unwave. So you're saying, but what is going on? Check, please. I won't derive this. You can ask me next time. It's not surprising. Remember, it's a pseudo-scalar, so there will be a gamma 5 interaction. There was a chiral symmetry. We can check that. But you are saying this is very different. But before I wrote, so I got this before I had G m over V psi bar gamma 5 psi. So what is going on? Which one is correct? Well, look at this, d mu G over V, psi bar gamma mu gamma phi psi is 1 over V d mu G psi bar gamma mu gamma phi psi minus G over V d mu psi bar gamma mu gamma phi psi. This is a total derivative. I can drop it. Can someone tell me what is d mu of this? What is d mu of psi bar gamma mu gamma phi psi? You will use Dirac equation, of course. Someone can do it quickly. What can come out? It's kind of obvious. I mean, after all, you're using I gamma mu d mu psi is m psi. So what will we get?
So something proportional to m psi bar gamma 5 psi.
Right. Because of the Dirac equation, obviously, the gamma phi will remain there. I think there is a factor of 2. So let's just, I like what you said, proportional, all we care. We can set down, when I said here, you know, there was a factor here. I should have said proportional. I didn't do the calculation, so I shouldn't have, I'm very sorry. So this was proportional, yes, of course. So let's call this a formulation A and the formulation B. A is equal to B. Doesn't matter which variables you use. Of course, the physics is the same. When you play, at the end, you will show that you have one and the same physics, okay? But it may be very convenient to know the variables. For example, in this formulation, you know that no matter what you do, it's going to be always 1 over V. And you know why? You also know it has to be d mu, because there was a symmetry. Remember, there was a symmetry. Phi goes into the I alpha phi. But I wrote phi as e to the I g over V, V plus H. So therefore, G over V goes into G over V plus alpha, or G goes into G plus V plus alpha. That symmetry tells me in this formulation that it must be derivative interaction, so that to keep the invariance. So see how it can be useful, this particular variable. But you get derivative interactions, and derivative interactions are hard to deal with, and therefore you are going to think twice whether you use it to do calculations. For example, if you want to do loops and so on, you would say, I'm never going to do that. That would be really crazy. So each variable, so in other words, the choice of variables corresponds to your task. Sometimes you want to see what is going on. And to see what is going on generically, for example, this particular formulation A is very useful. I don't care about the model, because when I write it like this, the interaction has to be derivative. So I have a generic property of the Goldstone bosons. They have derivative couplings, and they must couple it to the pseudoscalar current. You may take infinitely many different models. You will always get this from the physical reasoning. All the interactions will be derivative, and therefore I can learn something generically. But to do maybe a calculation, I don't want to do, especially the loops with the derivative couplings. I don't know how to do that. I didn't develop that particular, how to say, I don't know this in field theory. We don't like to work with such objects. So in a sense, really, it's not the question is which variables to use. what Weinberg meant is which variables to use when. I'm telling you today, but you will see it's going to make all the difference in the standard model. We will have to go from one variables to another. This is what that Hoff did and why he became so famous. The theory was developed by Lesho, Weinberg, and Salam, but they didn't know how to work with that. They got stuck completely. You could also say, well, you could say, you know, look, let's just finish on this note. Let's not start anything new. And this, obviously, I'm not going to pursue these calculations. Okay, this is just to give you a flavor. You could even say like this. You can say, okay, right, phi is v plus h e to the ig over v. And then you can say, why don't you then change the variables, go to phi prime, which is e to the minus ig over v. It's just a U1 choice, very funny. Of course, now I'm making it local. So this cannot be, of course, the symmetry. And sorry, no, I didn't mean this. Phi. So phi prime would be just v plus h. And you're saying, oh, are you getting rid of g? No, remember that psi l would then transform into I e g over v. There was a half, if you remember, psi l and so on. So it would reappear. You cannot get rid of it, okay? But you were saying, I don't like to have this guy at all in my formulation. My phi prime would be the following, but then g would appear here. And you would still get interactions, okay? So I'm just, okay, this just relax here. This is not so important. This will be obviously stupid to do here because I have a global symmetry. I had the symmetry only alpha is constant. And g, of course, is not a constant, so this is not a smart thing to do. But I could do it if I like. I'm just sort of giving you a flavor. I don't care which variables you like to use. You don't really, you know, just think, you know, when you're playing with it, oh, let me try to see in this variable, just sort of to get a kind of trust that you will always describe one and the same physics. And I can finish here. A few minutes earlier, hopefully there will be questions, but if not, at least we can eat earlier. I could tell you a lot more, but it's time for us to move to the Higgs mechanism. As interesting as physics is, it doesn't correspond to standard models, so I'll have to stop. It's not easy for me to stop, but I'll have to. Teaching is the art of choosing, and it's always a struggle. What to say and what not to say. Any questions? Okay. Then I see you tomorrow. That's it. You can leave. Have a nice
you.
afternoon. Talk to you guys tomorrow.